All right, so today we start with our next area of study that we're looking at. And so as you can see up here, it's called sequences and series. So the first sentence there, really, a sequence is a string of numbers which follow a pattern. So there could be any sort of pattern, could be a simple pattern or could be a complex pattern. There's all sorts of complex series, the Riemann series, and all sorts of real nerdy maths series. But for us, we're going to stick to something a bit more simple than some of those. So the numbers in a sequence are called the terms. So the terms, and the nth term is t with a little m. So t with, say, a 10 would mean the 10th term in that sequence. Now, there's a few different ways that we can write sequences. One, of course, would be using words to describe the sequence, but we want something a bit more mathematical. So there's two mathematical ways. So first one we're looking at here is a recurrence relation. And the recurrence relation tells us about the term in the next term in relation to the one we've got here. We do something to this term and we get that one. And then further on, we do something to this one to get the next one on, and so on. So here's an example of one. So the nth term is 3 times the n minus 1th term. So the nth term is 3 times the term before it. And term 1 equals 4. So sorry, you need to, so you're going to need to know how to get from one term to the next, but also you're going to need to know where to start. Now, this way here just says could also be written as the same in this way. So term n plus 1 is 3 times term n, and term 0 is equal to 4. That's not quite, so you'd have to actually, that wouldn't be correct, that wouldn't be for the same one, so you'd have to go back. Term 0 would be 4/3 in this case. All right, so term 0 is not actually part of the sequence, but that's where we start. So the reason that I've got this one up here is because that's what your textbook uses, but sometimes people write it like this. And when we get to a question, I'll show you where we can do this on the calculator as well. And the calculator uses this kind of way of describing things. All right, so the recurrence relation, how you get from one to the other, recursive formula, iterative rule. Don't hear so much the iterative rule term anymore, but certainly recurrence is the way that we think about it. All right, so how we get to next one from the next. So here's an example. So term n is term n minus 1 plus 5, and term 1 is 3. So term 1 is 3. So term 2 would be term 1 plus 5, which would be 3 plus 5, which is 8. And term 3 would be term 2 plus 5, 8 plus 5. Term 4, which of course is 13, is term 3 plus 5, which is 13 plus 5, which is 18, and so on and so on. All right. Now, the downside of this, of course, if you want term 10, you've got to keep going and doing all of that. You can use your calculator, and so I'll show you how to use the calculator. There's also a sheet, this one here, sequences in explicit relation. That's not the one we're doing at the moment. Recurrence relation, there we go. So there's how you do it on the calculator. So you should have that handout. It's on the website as well. But what we're doing is using our calculator. So here we are on the calculator. And so here's our menu. And on the second page of the menu over here, you see it says sequence. Click on that. Recursive, explicit. So we're on the recursive. So you can see here, as I said, it uses the n+1 and the n0. So for this particular one example that we were looking at, so this one here, so term n is the term before plus 5, and we're starting at 3. All right, so here's the calculator. So let me just clear all of that. So in here, n+1, so that's the next term, is this term. So you get from up here, so we've got this term plus 5. And then A0, well, see, we can change that. See here, n+1 to A0, A1, so term 1. So in this particular one, we have term 1. So I need to do that. So we have the previous term plus 5, and our first term was 3. See, now you need to tick on that. So now it's going to calculate for us down here in this table. And so to do that, click on there, and there we go. The first term is 3, second, and so on. So, and then there it's worked it out for us. So I've got it set at the moment to show lots, 40 in fact. All right, so there's your calculator. All right, now there's some things you can't do on a calculator that you've got to figure out for yourself. So find the recurrence relation for the sequence 9, -3, 1, -1/3. So we've got to figure out how can we go from 9 to -3. Well, we could take 14. That'd go to -3, but remember we've got to do the same thing each time. So if I take 14, I'm not going to get to 1. So it's not that one. How else could I get from there to there? Well, I could divide by 3. Well, if I divide by 3, I get to +3. So if I divide by -3, yep, that works. But if I go -3 divided by -3, yeah, well, that's 1, that works. And then the next one as well, 1 divided by -3. Well, yeah, we can write that as 1 over -3, which is, of course, the same as -1/3. So it's looking like to get from one to the other. So term n would be the term before it. Divide by -3. Now, generally, math, just say term n minus 1 over -3. Normally, mathematicians think that's a bit of a messy way of looking at it. So they'd say it's -1/3 times term n take 1. All right, for our sequence. All right, so I did mention about before when we did this one here, and I showed you on the calculator, you know, if you want term 40, you've got to follow each one through and work it out. So it's a bit of a mucking around. So it'd be nice if there was another way of working it out where you could just go straight to a term number. And there is, and this is what's called an explicit relation. So the explicit relation tells us, you know, to get term 50, this is how you get term 50. And it's written in terms of the term number. So for term 50, the number 50 would be involved in there somewhere. And so here's an example. Term n is 2 times n plus 1. So the first term is 2 times 1 plus 1. Second term, 2 times 2 plus 1. Third term, 2 times 3 plus 1. All right, and term 50 is 2 times 50 plus 1, which is 100, plus 1, which is 101. All right, so much more simple than working through and doing 50 terms and calculations in the explicit rule. All right, so the explicit rule may simply have the n in it, may have some other things in it. So here's an example. Find the rule. All right, so what we've got is term 1 equals 1, term 2 equals 4, term 3 equals 9, and term 4 equals 16. And so for this one, n equals 1, this one n equals 2, this one n equals 3, this one n equals 4. So we've got to think about how can we get 1 from 1? How can we get 4 from 2? How can we get 9 from 3? How can we get 16 from 4? But the thing is, we've got to do the same process each time. Like say, okay, well, you can get 1 from 1 by adding 0, but then you don't get 4 from 2 by adding 0. But if we do 1 squared, 2 squared, 3 squared, 4 squared, then we can get to those. So for this particular one, term n would be n squared. All right, so that's one form. It could be others. So let's have a look at another example. The height of a sand dune is increasing by 10% each year. It's currently 4 meters high. Find A, the recurrence relationship. All right. So for A, term 1. So now it's 4 meters high. Next year it's going to be, in the second year, it will be that 4 meters plus 10% more. 10% as a fraction is 0.1 times the 4. Now, you notice the 4 here is a common factor. (1.1) times 4, which is 4.4. Now, I'll get to the reason why I'm expanding that out there like that in a minute. Term 3. Well, term 3 is now the 4.4 plus 10% of the 4.4. And now this time 4.4 is a common factor, which is 1.1 times 4.4, which when you work that out is 4.84. So we're looking at how can we, say, get term 4 without doing what I'm doing here, because that's not really what I need to spend or expand. Sorry, I'm losing my train of thought. So instead of like going through here like I've done here and expanding all out, what sort of pattern is there? Well, when you look at this and see what sort of pattern it is, you'll notice that in this bit here, there's a 1.1 there. So term n looks like it's 1.1 times something, because it's a times next to it. Now, what's this something that it's times? Well, this something that it's times is the term before. So the term before is one term less, n minus 1. And where did we start? Well, we started at term 1 being equal to 4. So in terms of a recurrence relationship, well, there is our recurrence relationship. Now, the next one we're after is our explicit relation. So our explicit relation. All right, so I'm just going to develop that. I'm just going to change the colour of my pen. Oops. Change the colour of my pen. Let's go red. All right, so that's for part B. So explicit relation. All right, so the first term was 4. The second term up here is 1.1 times 4. The third term still got this 1.1 times, but it's times 4.4. And 4.4, so it's 1.1 times the 4.4, right? 1.1, that one, times the 4.4, but the 4.4 was 1.1 times 4. So when you get something multiplied by itself, that's 1.1 squared times 4. So let's have a look. So we've all got, oops, don't want that one. So when we look at the pattern, each one it's got a 4 in it. And we multiplied the 4, which is our first term, by something. Here we're multiplying by 1.1, here 1.1 squared, the next one probably 1.1 cubed, and so on. So when you look at the power here in the term number, power, that's the power of 1, and the term number, 1.1 to the 0, term number, what we've actually got here then, it looks like that our term number is 4 times, because there's a 4 in all of those, times 1.1 to the power of 1 less than whatever term number we're looking at. All right. So there's our explicit relationship. So our explicit relation, there it is. All right, and then the height in 7 years' time. All right, so here's a little bit trick. It doesn't say in the 7th year, it says in 7 years' time. So if we are at the start, I'll change my pen back to blue. So in 7 years' time, if we're now here in year 1, then in 7 years' time, it'll be in year 8. So that's term 8 that we're looking for. All right, so term 8, if we use the explicit relationship, would be 4 times 1.1 to the power of 8 minus 1, which would be 4 times 1.1 to the 7, which you can then get out your calculator and you can work that out. You can also do it using the explicit relation on the calculator, and I'll show you how to do that. So here's the explicit tab. So the explicit tab, this term was 4 times 1.1 to the power of n. And there it is. And so now I just need to get the calculator to calculate that. And there we are. 4.4, blah, blah, blah. That's what we got before. All right, so we're after term number 8. There it is, 8 point. Sorry, this is not to the n, is it? I made an error there. It's to the n minus 1. That's no good. Good thing I picked that up. All right, so let's go back and let's do it properly. 4 times n to the power of, and now I should put in brackets. It's not n, it's 1.1. What am I doing? Times 1.1 to the power of, in brackets, n minus 1. I think I'm starting to lose it. All right, that's better. Then here we go, term 1, 4, 4.4, and so on. There we go. So term 8, there we are, 7.7949. So 7.79, two decimal places I'll go to. So it's 7.79, and the height would be in meters. All right. Sorry, I hope I didn't confuse you there where I entered that in the calculator. All right, so that's it for the first exercise in the sequences and series. As always, have fun.